This video is for section 13-8, Powers of Binomials. In an earlier chapter, we would raise a binomial to the second power. For example, a plus b, and then squared. To do that, you do FOIL, and you'd end up getting a squared plus 2ab plus b squared. This actually is the shortcut way that I suggested you use for squaring a binomial. Square the first term, find the product of the terms, which is a times b, and double it, that makes 2ab, and then square the last term. With repeated use of the distributive property, we could raise a binomial to the third power, fourth power, fifth power, and so on, as shown in this pattern. So a plus b squared is that thing we just looked at. It creates a trinomial. A plus b to the third power can be figured out by taking this answer here, writing it in parentheses, and then putting another a plus b next to it and doing the distributive property. When you simplify the terms, it creates this four-term polynomial. A plus b to the fourth power makes this answer here that has 5 terms. Here you see the pattern repeat. Notice what's different is this has subtraction signs in here, and then when you look at the answers, you see how they're different. This one right here had a plus sign, whereas this has a minus sign. This second one here was all plus signs across there, whereas this one alternates, minus, then plus, then minus, and so on. So these patterns suggest to us that we could find out what a binomial raised to any power is as long as we can correctly extend the pattern. Here are some observations we can make from the patterns. The number of terms in the expansion is n plus 1, where n is the exponent. For example, when the exponent was a 2, 2 plus 1 makes 3 terms. And sure enough, the answer has 1, 2, 3 terms, a trinomial. When n is 3, the answer has 3 plus 1, 4 terms. And we can see that here. First term, second term, third term, and fourth term. So that's what this first observation is talking about. Now, second observation, if the binomial is a sum, that was these first 3 rows, right, a sum with a plus sign, then all the terms in the expansion are added. And we see that we only have addition signs in our answers. But if the binomial is a difference, that was these 3 examples, then the terms are alternately added and subtracted. And the even numbered terms are the ones being subtracted. So like in this example right here, a minus b squared, the second term, this one here, is the one being subtracted. The second term is an even numbered term. In the example right here, a minus b to the third power, it's the second term and the fourth term that have the minus signs in front. So the second observation here has to do with when there's a plus sign or when there's a minus sign in the answer. Third observation, the coefficient of the first term is always 1. And we can see that every time. It's 1a squared, 1a cubed, 1a to the fourth. The next observation, the coefficient of any other term is the product of the coefficient of the preceding term and the exponent of a in the preceding term, divided by the number of the preceding term. So that's a pretty complicated rule to describe that observation. What that's talking about is, what are your coefficients, right? This coefficient is a 1, this coefficient is a 2, the last coefficient is a 1 again. Or in this last example that's on here, this is a 1, this coefficient is a 4, this coefficient is a 6, and then we're back to a 4 again, and then we're back to a 1 again. That fourth observation is talking about where those numbers are coming from. Another observation, the exponent of a in any term is 1 less than the exponent of a in the preceding term. That's telling us that the terms are written in decreasing order of the exponents, right? In the very last thing, a to the fourth, but in the next it's a to the third, then it's a to the 2, and so on. The sixth observation, the exponent of the letter b in any term is 1 greater than the exponent of b in the preceding. So while the letter A is decreasing as you move across, the exponent on the B is increasing. There's no B here, or maybe you think of it as B to the 0, but now you have B to the 1, and then B to the 2, and then B to the 3, and B to the 4th. And finally, the sum of the exponents of A and B is always n. So in our very last example, where n is a 4, the exponents always add to 4. In this case, A to the 4th has a 4, and there's no B at all. But over here we have A to the 3rd, B to the 1. So 3 of the A's and 1 of the B's is a 4, which matches the value of n here. All of these observations put together will allow us to write out what's called a polynomial expansion for any binomial raised to a power. Now, what's the most complicated of the rules? I think it is Rule 4, the one that describes how to get the coefficients figured out. So wouldn't it be nice if there was a pattern or a chart that we could look at that showed us what all the coefficients are? And there is. It's called Pascal's triangle. And here you see it on the next side of your paper. It's credited to a mathematician named Blaise Pascal, but there were mathematicians from Asia that discovered the idea before him. Pascal's triangle has a lot of applications in math. In this section of the book, we're only going to use it to get us the coefficients of the terms in our expansions. The top row, or first row of the triangle, will give us the coefficient of a binomial raised to the 0 power. And remember, anything to the 0 power is just 1. So to say that the answer just turns out to equal 1 is no surprise. Now the second row we'll use when we have a binomial raised to the first power. Like if we had x plus y and we wanted to go to the first power, wouldn't we get 1x plus 1y, where these 1's are our coefficients? That makes sense to you, right? Now in this next row, we're going to use that whenever we have a binomial to the second power. And that fits our very first example from today's notes, right? We had a plus b and squared it, and we said that the answer was a squared plus 2ab plus b squared. The coefficients are 1, 2, and 1. And look at Pascal's triangle, 1, 2, and 1. Now this next row will be when you have a binomial and you cube it. The answer is going to have 4 terms, and the terms will have the coefficients 1, 3, 3, and then 1 again. So this one here will be whenever you go to the 4th power, and this row here will be whenever you go to the 5th power, and so on going down. Let's use Pascal's triangle along with those other observations that we made about the variables and the exponents to do some examples. First example, expand x minus 2y to the 5th power. We're going to match this up with the basic pattern a minus b to the 5th power. So we can see that instead of a, we're using an x, and instead of b, we're using 2y. When a binomial is raised to the 5th power, using Pascal's triangle, we see that our coefficients are 1, 5, 10, 10, 5, and 1. You need to remember those numbers, or I'm going to write them down just up here because they're kind of off the bottom of the screen. 1, 5, 10, 10, 5, 1. Now let's write the polynomial that's equal to this binomial to the 5th power. It's 1 x to the 5th minus, and now 5, I'm getting the 5 right there, and then x to the 4th, 2y to the 1st. Then it switches to a plus sign, and now the coefficient is 10, and it's x to the 3rd, 2y to the 2nd. Now it switches back to a minus, and the next coefficient is 10. It's x to the 2, and then 2y to the 3. Then it switches to a plus, and we're back to a coefficient of 5. And it's x to the 1, and then 2y to the fourth. Now the sign switches to a minus, and our coefficient is 1, then x to the 0, which I'm not even going to write, and 2y to the fifth power. Before simplifying the different terms, let's talk about where these parts came from. When a binomial is raised to the fifth power, I know that there is 5 plus 1, or 6 terms, and the coefficients of the 6 terms come from that row of Pascal's triangle, the 1, 5, 10, 10, 5, and 1, which no doubt you see those coefficients in the different terms. Another thing I know in my answer is that when there is a minus sign, that I'm going to alternate signs in my answer, and that the even numbered terms will get the minus signs. So the first term's positive, but the second term gets a minus in front. The third term gets a plus sign in front, but the fourth one gets a minus sign in front, and so on. The next thing I know about my answers is that the very first thing in the parentheses, earlier we were calling that the letter A, will get raised to the fifth power, whereas the second thing in the parentheses, the 2y, will get raised to the 0 power, and that creates the first term right here. Then what happens is that the exponent on our first term decreases each time as you move to the right, until finally in the very last term, it would have just been x to the 0 power. But the exponent used on the value of b, which is the second thing in the binomial, increases as you move across term to term. So in the very first term, we had the 2y to the 0 power. I didn't even write it. But then we have 2y to the 1, then 2y to the 2, 2y to the 3, and so on until in the very last term, it's 2y to the fifth power. The exponent matches the exponent on our binomial. Once you've written out the different work to create the terms, what's left now is to simplify. So this is x to the fifth minus 10 x to the fourth y plus 40 x to the third y squared minus 80 x squared y cubed plus 80 xy to the fourth minus 32 y to the fifth. Now, where did these numbers come from? I used the exponent rules from earlier this year. In the middle term, 2y was raised to just the first power, so that's just 2y. So 5 times 2 is 10, and then we have the x to the fourth, y to the 1. When working on this piece right here, I had to do exponents before doing the multiply. So 2 to the second is 4, which I then times by 10, making 40. And then we had x cubed and y to the second. When working on this piece right here, again, you have to do the exponent before you actually do the timesing. So 2 to the third is 8, and 10 times 8 got me the 80, and so on. Let's do one more example. This time we have 3 plus y squared raised to the fourth power. And again, let's take a look at Pascal's triangle to see what our coefficients will be when raising to the fourth power. They will be 1, 4, 6, 4, 1. I'm going to jot that down so I don't forget. If it helps you, you might also want to identify what's the first thing in the parentheses and what is the second thing in the parentheses. We were calling them A and B in general when working with this lesson earlier. Now let's write out our answer. We have 1 times 3 to the fourth power times the y squared to the 0 power, which I'm not even going to write down. Then a plus sign. And now the number 4 from Pascal's triangle. Now we will have 3 to the third power and then y squared to the first power. If it helps you to keep track, you might put the y squared in parentheses and write to the first power. Then we have a plus sign again, and now a 6 from Pascal's triangle. Then we have 3 to the second power times y squared to the second power. Notice what's happening to the exponent I'm using on the 3. It's decreasing. It started with a 4, then a 3, then a 2, and so on as we move to the right. Look what happens to the exponent I'm using on the y squared. It's increasing. Y squared to the first, then y squared to the second, and so on, moving to the right. Let's keep going. We have another plus and then a 4. Now we have 3 to the 1, and then y squared to the 3. And then another plus sign and then a 1 from Pascal's triangle. This time we would have 3 to the 0 power, which I'm not even going to write, and then we'll have y squared to the 4th. Now let's simplify our terms. 3 to the 4th is 81, plus 4 times 3 to the 3rd, so that's 4 times 27, which is 108, y squared, plus, now we have 3 squared, which is 9, so 6 times 9 is 54, y to the 4th, plus, now we have 4 times 3 is 12, y to the 6th, plus, and then finally we have y to the 8th. So this polynomial with 5 terms is the expansion of this binomial raised to the 4th power.